So hello, welcome back to Advanced Image Synthesis. And let's start with a quick reminder. So there's still the lecture evaluation open. So if you're a student of the University of Duisburg-Essen, please go to Moodle at the end of this class, not right now, at the end of this class and fill out the evaluation form. So far we have very few entries, so it would be very helpful if we get more input on what you like, what you don't like, and just let us know how well I did, I guess, mostly because I gave all of the lectures. So I'll remind you again at the end of this session, and yeah, please go ahead, fill it in. Okay, now that that's set, let's look at another topic, compression, or more precisely, image compression. So why do we care? Why do we care in image synthesis about image compression? Well, it's not synthesizing an image, right? It's just taking an image and storing that. Well, it turns out that compression and also decoding or decompression is today an integral part of many rendering systems. Data gets big, images get big, other resources, not just photographs, pictures here, such as the LENA image, they tend to get larger and larger. And while we have more and more compute power, the bandwidth doesn't quite grow that well. So the bandwidth either from background storage, from network storage, or just any internal bus system doesn't really keep up with the compute power that we gain. So it makes a lot more sense to first crunch things together and make them smaller, then send them over the bottleneck bus systems and then decode them as late as possible. So today, decoding images has become a part of the actual rendering process and not just a pre-processing thing that you do well and then it's just fine. Okay, so it makes quite a lot of sense to consider that and at least understand the basics of compression techniques to better understand the implications of using one or the other technique. So here's an example. So what you see here is an image. It's a background image. I think it's a background image from some older macOS version, just the standard image that macOS came with. And you look at the file, it's fairly high resolution, so it's about 3000 by 2000 pixels. Every pixel is stored in 8 bit per channel, so it's red, green, blue. Gives you a total of 24 bits per pixel, and if you do the math, you'll see that that should consume about 80 megabytes in size. Now that's just a single image. Now imagine a movie that running, I don't know, 25 hertz or so, so that's quite a lot of data even for a modern computer system. Now, if you look at the file as it's stored on disk, you'll see that it's roughly 2.5 megabytes in size, and it's stored what's called high quality JPEG image. So if I would scale the image down by a factor so that this image here corresponds to the size, it would shrink quite considerably. Of course, both images have the same size. The latter one here just occupies less space. But you can see it occupies significantly less space on disk or less bandwidth. So apparently the whole thing works. So it seems like JPEG, the format that is a very popular format, in particular for photographs, seems to, well, crunch things down quite a little bit. So how does that work? Okay, so before I want to talk about how that works, let's just basically classify compression schemes. So generally in data compression, we can always distinguish between lossless formats and lossy formats. So while lossless formats just reduce the data in size, or most of the time reduce the data in size, they preserve the original data like bit by bit, assuming that nothing went wrong. So that's one of the other things that I don't mention here explicitly or don't discuss here explicitly, but I could briefly mention it. Data, when it's in compressed format, is generally way more prone to defects. So if there's anything going wrong in the transmission of a compressed data stream, this might cause significantly more trouble than in the uncompressed stream, which is kind of clear. If you compress more data to fewer bits, if a bit gets lost, then it's going to wreak more havoc. But that's not what I mean here. So lossless basically means if nothing goes wrong in the storage and transmission, we get exactly the same data back bit by bit. Whereas lossy means even if nothing goes wrong, we still destroy some of the data. And the idea is to, well, just lose pieces of information that are not important or not so important, whatever that means. Okay, and lossy compression is often used in images and movies, moving images, or in audio compression. That's also a typical regime where you would do lossy compression. If you would write a piece of text, you would probably not like a lossy compression, right? Every now and then, maybe a word, if it's not so important, being wrong, or I don't know, a few words out of order, or a period missing, it's probably not the way to go. And it gets even worse. Like if you think about a mathematical computation, right? I mean, every now and then a number wrong doesn't work out, okay? So it only works for specific cases. Now the question is, why would we even care about lossy compression if we can compress everything and preserve the actual data? Why would we even dare to lose data? Why would we even care? And the idea is that, well, if we are willing to lose a little bit of quality that is potentially unnoticeable, but we can compress the data significantly better, like orders of magnitudes higher, then we might actually be willing to consider this. And as a matter of fact, this is sort of the standard. So lossless compression is actually relatively rare in graphics. So there's very few cases where you would actually use lossless compression. And as a matter of fact, the stream that you're currently viewing is compressed with a very high degree of data loss, both the audio stream as well as the video stream, and still, well, you get the idea, I suppose, right? Maybe my body is lost, but that's pretty much it, right? So you get the overall idea, and that's what matters in the end. It's better than not getting the data at all. Okay, so what lossless compression schemes do we have? There's really a myriad of compression schemes. There's a ton, and I just want to discuss a few basic schemes because they play a pretty important role. So first of all, there's the run length encoding, or in short RLE. Then there's a ton of LZ compression. So that's basically named after two researchers, Lempel and Ziff. And well, then later on, a person called Welch joined in the team. So we also have a LZW compression scheme. In particular, LZ77 is a very important compression scheme here. And LZW as well. That's why I want to talk a little bit about these two compression ideas in more detail. And then there's Huffman coding as another interesting idea to reduce the size of data, which in particular, in combination with LZ77, for instance, is part of what we call deflate, which in turn is the number one compression scheme that you would use when you create a zip file or when you create a PNG file. Both are based on a combination of LZ77 and Huffman coding. So it makes sense to look at these in particular. And some of these, as you can see with zip files are not specific to images, right? I mean, they get used in pretty much any data compression approach. So some of those techniques are used in general compression, and some of those are somewhat more specific to images. All of those are lossless, however. That doesn't mean that these lossless approaches aren't combined with lossy approaches. As we will later on see, a similar idea to Huffman, which by the way is spelled with the one N, so that's a mistake here as I just noticed. A similar idea to Huffman coding, entropy coding, is also used in the JPEG format. It's not directly Huffman coding, but it's a very, very similar idea. Okay, so let's start with run length encoding, right? It's a fairly old idea. It's been popular for a while. Very old or older imaging formats such as BMP support run length encoding. And again, even newer ones such as JPEG also has a run length encoding concept built in, combined with this entropy thing. So what is run length encoding? And the idea is simply, well, to encode the run length, to encode how often a symbol appears along with a symbol. So as an example, say we have a bunch of W's, B, and then a bunch of W's and a few B's. For instance, that could be white and black. We can write them out just as they are here, but as images go, they often have uniform regions. In one scan line, we might just have 10 of those white symbols in succession. So we might as well write, okay, now please 10 W's, and then one B, and then another 10 W's, and then 3 B's. Okay, so as you see, this version here is significantly smaller than that one, and it might work even better with even larger regions. So sometimes you might have, I don't know, 100 pixels that have potentially the same color because it's background. I mean, just look at the slide here, that very slide here, right? It's almost entirely black except for a few white pixels and, well, then me at the bottom here having a few colored pixels, but that's pretty much it, right? So if we would encode that in a scanline approach, I mean, the first probably 50, 60 lines are all entirely black. So those could be encoded extremely quick. So now the trouble here is, if we want to decode this 10B, 10W, B, 10W3B, we need to make sure that the 10 is recognized as, well, this counter, okay, now come 10 Ws, okay, and not just a 1. I mean, there could be a 1 in the data stream or a 0 in the data stream, right? So we need to recognize that. And how would you do that if, well, numbers are allowed to show up? So one simple solution is introduce a special character that says, okay, well, now we got a counter coming, okay? So for instance, if we encode the sequence here, and you see that there's a 1, 2, 1, 2, and then there's a bunch of ones which you would like to crunch together. So you would like to say, okay, well, now there's 9 ones, okay? And one way to achieve that would be to introduce this x here and say, well, okay, if we've got an x, the following character is a counter, or the following n characters are counters, and then we have our element, our alphabet entry character that we actually want to insert 9 times, and so on and so forth. Now, the trouble with that is, well, what happens if that X appears? I mean, I said we invent a new character, but you can't really invent a new character, right? If you have a binary stream, then every bit pattern, right? Say we have 8-bit characters, then all 256 characters could be used, could appear in the data stream. Okay. So how do we deal with that? Well, we can still say, okay, well, there's this reserved thing. And if an X appears, then please interpret the next number as counters. However, if an X actually appears in the input stream, we have to somehow flag that. And the easiest way to fix that is to, well, say, okay, we've got 2 X's. Okay. So we just say, well, XX means the next character is an X. Well, you could technically do that as well. You could say, well, X1X. So that would probably also. But I guess my XX version is 1 character shorter. Both works, but there's one thing, and that's one important thing, and that's why I kind of spend so much time about this seemingly little piece of information here, and that is, this can happen. And what happens here is that the data stream that is compressed is larger than the data stream that is uncompressed, which seems pretty stupid, assuming that I want to compress data and make it shorter. So why would I possibly blow things up? Well, the answer is that always has to happen. I mean, that's an entropy argument, and if you're interested more in entropy coding, general compression in the theory, that's not what I want to cover here. That's probably going to be covered in data structure. No, it's not data structure. It's probably theoretical basics of computer science, I guess, in that case, or information science. That's where these things are covered. But there's a very simple argument, a counting argument that says, if you compress data, there always have to be a significant amount of cases where things are actually bigger after the compression than they were before. Okay, so yeah, German is my native language, but this is an English lecture, so I try to do my best to speak something that remotely resembles English. Okay, okay. Now, keep that in mind. We'll stumble upon this basic idea of our compression actually breaking things. We'll always stumble upon that, and I'll make some remarks along the way. Okay, so here we go. Let's start with LD77, Lempel-Ziff, 1977. The 77 is simply the year when that thing was invented. Very important compression scheme, and it's a relatively simple compression scheme as well. Okay, so it's built on the basic idea of 2 things, a so-called sliding window and a look ahead. Okay, so let's take a simple example. Let's assume we want to compress the string ananas. Okay, so here it is, and you can see it's got a ton of redundancy, right? There's A. So a ton of A's, a few N's, and there's this sequence of A's and N that also follow. So there might be quite a chance to shrink this down, and there is. So the way this works is as follows. We stream the data through our encoder, and we use these two things, this sliding window and this is the sliding window, and that's the look ahead. Okay, so in here I've chosen the look ahead as 4 byte and the sliding window as 8. Usually you make that significantly bigger, but well, I want to get things on one slide, so that's why I make them pretty short here. So let's just say we have an 8-bit sliding window and we have a 4-bit look ahead buffer. So now what we do is we start with our first character, which is an A, an ananas, it's an A. And so far we haven't done anything, so we'll just output the A, but we'll add 2 things to the A, 2 numbers, both 0. Okay, and I'll explain in a second what those are good for. At least for now, they're pretty useless, and they blow up the data stream. Again, notice that we turn 1A into, well, 2 zeros and 1A. So that pretty much blows it up by a factor of 3, which is significant, but it's unavoidable. Okay, now comes the next character, which is an N. And again, the same thing, not much we can do, so we'll add 0, 0, N to our output stream. Okay, so the next thing we do is we'll have to deal with another A and another N. And now we can be a little bit clever, okay? Because we've seen AN before, right? We've already seen an A, we've already seen an N, and we intend to encode another A and N. We can make use of that previous occurrence by actually not writing out 0, 0, N, but finally using those 2 characters. Because what do they mean? If they're not 0, 0, they mean the following. They mean, in my sliding window at position 6, 6, 2, please copy 2 characters from the previously seen data and then add an A. Okay, so now with 3 characters, we get 3 characters, right? We get the A, the N, and the A, which is still not really a compression, right? I mean, it's just the break-even point. But as we proceed with the data, so the final S, we can't really turn that into anything useful, so we again output 0, 0, S. But you can see, if sequences in our sliding windows reappear in the look-ahead buffer, we can compress those, or we can represent them by just 2 numbers. Okay, so we'll just add a character where they appear, and we'll just add the length. Okay, so I guess I'll just need to do a few minor adjustments here. Okay, so I think we got that covered. Good. Okay, so that's ananas. So what we output are basically 4 tuples. 3 tuples. And again, notice how we've encoded 1, 2, 3, 4, 5, 6 letters with just 4 tuples. However, every tuple is pretty big. So that's maybe not a really great idea. Okay, shouldn't there, is there a mistake in the 3rd row? No, there's no mistake in the 3rd row. I'm pretty sure that there's no mistake here. So we've covered the A and the N, and the next character is again an A. So that's perfectly fine. And then we got the final S here. Okay, so the character here is always the one that follows the sequence encoded by the first 2 numbers. And the 6 and 2 encode A and N, and the next character is an A. Okay, so that's pretty much it. So you can't really do 6, 3, S because you haven't seen the A yet, the following A. Okay, so notice how we've decreased the output in terms of tuples, but well, every tuple is pretty big. So overall, we've blown up the data, which is something that I mentioned can always happen in a compression scheme and has to happen in any compression scheme. Okay, but we'll take care of that later on due to the aforementioned Huffman coding. But let's for now ignore this issue here. And as a matter of fact, in practical implementations, you usually have the situation that LD77 alone actually reduces the data by some considerable amount, because even though you blow things up, you find these tuples pretty often. You find non-zero. You can generate non-zero entries fairly regularly. But let's look at how to decode the thing. So if we're decoding the thing, okay, then all we have is 00A, 00N, 62A, 00S. So that's what we get as transmission, and then maybe, I don't know, an end byte or something that terminates them. Okay, so how do we decode the data? Okay, so do we have a reasonable question here? For now, the connection between the last two lines makes no sense from a programming point of view and has nothing to do with the topic. Okay, sure. I don't know what exactly that's supposed to mean, but anyways. So we get those 4 lines at the receiving end, and now we need to be able to recover the original string because otherwise it wouldn't be lossless. Okay, let's see. What do we do? Well, we start with 00A. So every time we hit a 00, we'll just output the character. And observe 2 things. We output the character and we keep the sliding window around, and we also output it into the sliding window. So beside the fact that we output A, we also output an A into the sliding window. Next, we have 00N. So we output an N and add it to the sliding window. So we now have AN in the sliding window. If we then see the 62A, we can actually go to position 6 here, copy 2 characters, and add an additional A. So get a total of 3 characters ANA. And those we append again to the output and the sliding window. Finally, we see 00S, and voila, there's our S. We're good to go. Now, as you can see, we were able to recover the entire data. Now, if we would have, as Q said, I mean, he didn't suggest it, I'm pretty sure he knows that was wrong, but just from a conceptual point of view, if we would have written 6.3 here, right, we wouldn't have been able to decode anything at that point, because that would have said, okay, well, at position 6, copy 3 characters. And the simple answer is, well, there are only 2 there. Which one should I pick at the decoding end? Okay, so anything that you haven't seen yet that's in the look-ahead buffer, you can't use that in the compression scheme, obviously. Okay, so nonetheless, we were able to, voila, get everything decoded just fine from the 4 tuples. Okay, so, and also notice that the decoding is fairly simple. Okay, it's actually that simple. We just go through this buffer, through the stream of tuples, and then just have to do simple successive copy operations from our look-ahead buffer. So it's actually an extremely fast decoding that we can also perform here, which is nice if we want to do this in real time, right? Remember, we're doing computer graphics here, so we want to potentially decode that in real time. And that's also interesting, it can be integrated into actual hardware pretty easily. So now, what else can we do? So there's a couple of things that are fairly interesting and that make some of those compression schemes interesting, or they're just interesting ideas that you can add on top of compression scheme to just make better use of bits and bytes, which is an obvious requirement for a compression scheme. And LD77 has such an idea. And there's a couple of nice quirks to it, but one thing that I found particularly interesting is encoding theory for, or encoding concept for periodic entries. So for instance, if your input is just 0, 1, 0, 1, 0, 1, okay? Then you can do one fancy thing, or that's what LD77 allows you to do, and that's you can choose a size that actually goes beyond the size of the sliding window. So for instance, if I want to encode this sequence of n 0 1s, I start with a 0, so there's not much I can do. So again, end with 0, 0 and the character 0. 0, 0, character 1, that's the first thing. But then I can do something very nice. I can say, okay, starting at position 6, give me n minus 2 characters. Okay, starting at position 6, so that's position 6 here, I only have 2 characters. So if that, for instance, says, okay, give me 10 characters, what the system's supposed to do and what the decoder does is it goes 1, 2, warp around, 3, 4, warp around, and so on and so forth. So this way, recent periodic entries can be encoded without specifying those. And the idea is simply to make better use of the second number here, right? Because the second number, if we wouldn't allow something like this, the second number would always be relatively small, right? I mean, it could only be, well, the position where we are to the end of the sliding window, right? And we would waste a bunch of bits. So there would always be numbers that we can't make use of. All right, so bigger numbers than this difference. And that's one of the nice things that are added to the LD77 concept, is to make use of those kind of lost bits and allow for such encoding. Give those technically invalid situations, give them an actual meaning. Okay, and then we can decode. Of course, we need to observe this during decoding, but we can still decode it. So that's all nice. What are issues or challenges? Well, challenges are to find, in the encoding process in particular, to find the proper place, right? So for instance, if you encode that stream here, let's just say we encode this 0, 1, 2, 0, 1, and so on and so forth. We encode this up to a certain point before the 6. So notice that after the 6, there's 0, 1, 0, 1, 5, right? And we could, if we look this up, we could say, okay, oh, we got a 0, 1 pretty much at the beginning here. Right, so we could reuse that 0, 1. We could say at position 0, copy 2 characters. Or we could search a little longer, pretty much the entire string, and say, oh, well, we can do a little bit better. At position 3, we've got, position 3 is about here, 0, 1, 2, 3. We got 0, 1, 0, okay? And that's what we could use. So we could copy more characters, 0, 1, 0, 1. We could actually copy 4 characters and then add the 5. So the second one would certainly be better, but we would have to search for longer sequences. We would have to make our look-ahead window bigger, right? If our look-ahead window is small, we would probably never have looked at the 0, 1, 0 at all 4 characters. So long story short, if you're willing in the encoding process to use more memory for bigger windows and use more computing time for longer search, you can get a better compression rate. And that's pretty much what you get when you run your compressor, when you run zip and you tell it to like do a quick compression or do a better compression or an average compression. Those are things that you vary, right? The search and the sizes. Those are things that you vary when you fiddle around with those parameters, okay? So there's obviously problems with that as well, and a particularly bad example would be a sequence of just characters one after the other, no character ever repeating. Okay, in that case, we would blow the data up significantly, because all we can do really is 0, 0, and then the character. So if the number of characters, a number of different characters that varies, is bigger than our window, right? We could never ever reuse anything, and we would simply blow up the data by some factor. It could actually be worse than a factor of 3, because these numbers might actually be stored in, well, more than 8 bits. Right? If your window is big, then they might be more than 8 bits, and then in that case, you might end up blowing your data up significantly. And again, that always has to happen. It's a bad situation, and we need to deal with that. And there's some ways to deal with that. For instance, you could detect whether your compressed stream is bigger than your uncompressed stream. Okay, so you run your compression, you check how many bytes did I get out, and if the result is bigger, you would simply not compress it at all. Okay, send the uncompressed data, because it's apparently better. However, you need some additional flag then. You need to add a flag that says, okay, well, the data stream that's coming is compressed or not. So you have to add another bit to it, right? So you have to add another bit to everything. To any compressed stream, you have to add this bit that says compressed. And to any uncompressed version, you also have to add a bit that says uncompressed. In any case, you add data to it, right? So you can prevent data growth, at least in some situations. So data might always grow in some situations. Face it. Okay, that's, the good news is in most situations, actually, it doesn't grow. In most situations, you have some structure in the data. If you have perfect noise, that's probably a relatively rare occasion. Huh? Okay, so much for LD77. But we'll later on come back to LD77. Just keep in mind, we've got these nasty situations here with those tuples. But one important thing, which will be important later in particular, is these tuples also have a structure. Right? Notice it's all a bunch of zeros that we add. So it's not the additional data that we add to the stream that causes headaches here. This additional data has structure again, and we might be able to make use of that. Okay, but let's stick with the LDs for a second, and let's look at LDW. okay, which is called Lempel, Ziff, Welsh, or which is the abbreviation for now Lempel, Ziff, and Welsh, okay? And that one is used also in a popular format called GIF, Graphics Interchange Format. You've probably heard about GIF before, right? Animated GIFs. Those are still somewhat popular, and GIFs use LDW, okay? So that's also something that gets used. So how does that work? And the idea is a little bit different, or it's very different actually, is to use some sort of a larger code book, as it's called, a larger character map than the original character map. Let's say our original characters are 8 bits. Okay, so one character is usually encoded as 8 bits. Let's say we'll use 12 bits. Okay, we'll just have 4 more bits. Obviously, 4 more bits is a ton more data, right? It's 2 to the 12th power as compared to 2 to the 8th power, right? So that is 4,000 compared to roughly 256. So those are a few more combinations that you can store. Okay, so now what do we do with that additional data? Well, we do the following. So if we want to encode something, let's say we want to encode the string LZWLZ7. Okay, so that's supposed to be our input. Okay, so here's our input, or that's the prefix of the input. Let's say the data continues a little bit, but that's how it starts. Okay, so what we do is the following. We again start with the first character, and there's not much we can do except store the L. Okay, so we store the L and we also output the L. But in addition to that, we do one more thing that is not part of the output or anything. That's just something of our internal data structure. We'll create a new entry in our code book, our 12-bit code book, like the 257th entry, so to say. And that entry contains LZ. So it's got the index 256 because we start at 0, right? And we store LZs there. Okay, so we store 2 characters at that point. Now we approach the next character, which is a Z. And again, we can't really do anything reasonable with Z. So we'll again just output the Z, but we'll in the background create a new entry. This is now the entry with the index 257, and that's ZW. It's simply Z and the next character, which is ZW. Okay, now we encounter the W. Again, nothing we can do. Notice how we haven't really seen anything before. So we'll just stick with sending the data as it is. Now it gets interesting. After the W, where we create a new entry WL, we hit WL, okay, because we got LZWL. Okay, so after the W, we encounter LZ, and we've encoded LZ before here. Okay, so we now have one entry for 2 characters. And that's what we output. So we output the 256, which represents LZ. So I've written LZ beside that, but the only thing that we output is the 256. Okay, so we output the ASCII code for L, up with 12 bits. So there's going to be 4 bits wasted. We output the Z, again, ASCII code or ANSI code for Z with 4 bits wasted. A W code for W, 4 bits wasted. And now 256, and that stands for LZ. Okay, and then finally a 7, which we've seen before, so we simply output the ASCII code for the 7 and again encoded in 12 bits. Okay, so and then let's say we're done. So we might continue for a while, but let's just pretend we're done. So what we send is just an L, a Z, a 256, and a 7. Okay, the code book itself on the right is never transmitted. Okay, so we need to be able to recover that code book to make sense of the data on the receiver side without ever having it. Okay, let's look at that. So let's look at the receiver side. And what do we receive? Well, we receive LZW256.7. Of course, LZW and 7 are also encoded as their ASCII codes, but I wrote them here as characters. Okay, let's see if we're able to decode the whole thing to recover the original LZW, LZ7 sequence. And indeed, we can. So we start with the L, well, just an L, so we'll output that. Okay, first character does nothing else. Second character is a Z. Again, we output the Z, but now we again built from the last character and the current one, we built a new entry in our codebook. Of course, the first 256 entries, so from 0 to 255, those are just the regular characters. So again, we build that LZ code, then we see the W, we output the W and build this ZW from the last output and the current character and append that to our codebook. Now with the 256, we've already generated that. What a coincidence. And we can output LZW. to the output stream, and then when we see the 7, we again create a new entry with a previous entry, and with the 7 appended to this. Yeah, so it's really a nice idea that we kind of build this codebook on the fly, and we never have to transmit it because we can rebuild it on the receiver side. And the hope is that sequences, that these codebook entries, as you can see, they grow, right? So at first they're all 2-digit entries, and then as we reuse 2-digit entries, we'll get 3-digit entries, and so on and so forth. So they will grow and grow over time, but we also run into a couple of issues here. Okay, and that is what happens if our codebook suddenly contains 4,000 characters, so 12 bits of data. And there's a couple of things we could do. So we could just stop building new codebook entries, which is one solution, or we could just delete the codebook and just start from scratch. So that's the first thing. So what do we do when the thing overflows? We reset it, or we don't add anything. So generally, you actually reset it. The rationale is that coherence is often local. So something that appears multiple times often appears nearby multiple times. So you want to basically create a new codebook. But again, you can detect this on the receiver side just as well as on the transmitter side. If it overflows, simply do a reset and start the process anew. What's nice about this is it's super simple, right? There's nothing we need to search for. Okay, there's no search, right? We don't need to search through this sliding window, find string sequences, right? It's a very simple deterministic technique. So it's both the encoder as well as the decoder can only be implemented in one way. Again, that's different from the LD77, right? I mean, there I was kind of free to pick wherever I wanted. So determinism is also a nice feature because it allows you to validate things, compare things, even in compressed format. Right? It's even easier to integrate that into a silicon to build hardware that actually codes. On the downside, again, we blow things up, right? Every character is stored as 12 bits. Besides the fact that actually handling 12 bits and when only 8 bits are addressable are kind of a little bit of a nightmare if you implement that. But regardless of that one, it might happen that we have to encode every character again with 12 bits or whatever we choose. You can also choose 14 bits. You can choose whatever you want, but 12 is a pretty natural choice. We add, well, 4 to 8 bits, which is, well, half of the data might get added. So again, there's a potential for the data to grow in the compression process. See that there's this unique thing that kind of goes through anything. So another issue is that this very method was patented until 2002, which is probably not an issue anymore, right? Given that that's about 20 years ago, but it was a pretty big deal, right? In some areas, it was even under patent until 2006. I think that 2002 was US and that's Europe or vice versa. I can't remember. But in any case, it was patented and actually companies fought for that patent. So, and that was quite a big deal when the internet, right? 2000, internet, becoming very popular, GIF being, well, the standard for images, not just animated images, not these little annoying animated GIFs, but they were actually the standard for imagery on the internet. And then the decoding and encoding was under patent protection. So that was quite a big deal. What happened was that, well, people started to think about, can we just program something that doesn't require use of a patented algorithm? And the outcome was PNG, which is now the most popular compression format for images when it comes to lossless compression. Okay, so we got a question. You don't understand anything. That's bad. Is that why PNG Series 10? Well, so I mean, there's a couple of things about PNG and GIF which makes them pretty hard to compare. One is that they use a different compression scheme, but the other thing is that GIFs, for instance, they only support 256 colors, whereas PNG support pretty much as many colors as you want. So it's not just the compression that was improved. Actually, the PNG compression is generally better than a GIF compression, but there's a couple of other things that were added. So that makes them pretty hard to compare. I mean, the only thing that's totally obvious, I guess, if you take an image, normal photographic images and store it as GIF as compared to a PNG, is that the GIF will look significantly worse. Why? Because it has to rely on 256 colors. It can pick those freely, so it can choose which colors out of the 16.7 million 24-bit colors, but it has to stick with these colors. So it has to use dithering for most images, and that will look crappy, to put it simple. I guess around in the 90s or the early 2000s, that wasn't a big deal because we were used to like 256 colors being kind of the limit. But these days we're using 24-bit colors, so you wouldn't store a photo as a GIF file. It's going to look awful because of those 256 limitations. So when PNG was developed, it didn't just add a new compression scheme to get rid of that silly patent issue. It added a couple of other things. Among those things, it also added animations, but the founders of the PNG format made, I would say in hindsight, one crucial mistake, and that was they devised two image formats. PNG, the one that everyone uses, and then I think it's called NMG, which is just PNG plus animation capabilities, okay? And the thing is, I guess, historic thing that happened is everyone read the PNG specification, was like, oh, cool, let's implement that. And no one kept on reading the specification of, oh, how can we make this animated? So people stuck with GIFs for animations. So I'm not even sure if browsers actually support animated PNG, so the NMG format. I've never tried, and it's very unpopular. And it's really a pity, since when it comes to like animated imagery, we're still stuck with this ancient GIF format, which is not under patent protection anymore, but still looks crappy due to the 256 bit restriction and a couple of other restrictions. So no transparency. There are a couple of other issues as well. Okay, so it's really sad. But anyways, that's history. That's how history works. Not necessarily the best format succeeds. So, that's LZW and that's GIF. Let's forget about that now, and let's go to more modern things. And I mentioned a couple of times there's this idea called Huffman encoding. Okay, Huffman encoding is an entropy coding method that basically means that you try to reduce the number of bits for a character, for an entry in your alphabet, so that characters that show up more often are shorter and characters that show up less frequently are longer, so that on average your overall bits required to store your characters are fewer. So we'll now actually modify the bits per character. Okay, so the input is given a set of characters, okay, so your alphabet or symbols, and some probabilities or frequencies, whatever you want to call it, right? You either say, okay, 1 out of 1,000, or you say 1,000, which is kind of the same. Okay, so you know how often these things show up. And what you want to find is a code, and in particular prefix-free code, I'll talk about that in a second, that minimizes the overall length of the encoded string. So that means things that show up often should have a shorter representation. Okay, so let's look at an example right away. Let's say this is our input here. We have an input, or that's our character set A, B, and C. And C shows up pretty often. Okay, so we want C to be shorter. Okay, so let's say C shows up twice as often as an A or a B. Okay, so I just want to store C with 1 bit, and an A and a B with 2 bits. Okay, so and then just pick whatever, 1, 0, and 0, 1 for A and B. Now, if I choose that encoding and I transmit 1, 0, 0, 1, 0, I have a problem. If I transmit it this way, there's 2 ways to split the stream up, right? It could either be 1, 0, pause, 0, pause, 10, which is ACA. Or I could split it differently, so I could pick the first 2 characters, but then the second 2, and then just the final one. So 1, 0, 0, 1, 0 also makes perfect sense with regard to that alphabet here. But it's a different outcome. Okay, so we run into issues here. How could we fix that? Well, one is to actually introduce separators in between, right? We could say, okay, here's the first one, separator, second thing, separator, third thing, separator. Just like the X in the very beginning. Okay, remember when I introduced this X as, okay, for the run length encoding, when we wanted to start, where we wanted to specifically mask this number character. Okay, but the problem with that one, this X again would have to be encoded and would consume memory. So maybe not a great idea. So what we want to do is we want to use what's called a prefix-free code. Okay, so what's a prefix-free code? And that simply means that none of those bit entries here, the 1001 or the 0, none of those should, and that's not what's happening here, but none of those should be a prefix to another one. And here you see the issue. The 0 for the C is a prefix to the B. So the code for B01 starts with the code for C, namely the 0. I could fix this simply by choosing A as 10, that's fine, but B as 11, and then C as 0. So if I change just the code for B to 11, this works perfectly fine. Because whenever I start with a 0, I know this can only be a C, because none of the other two codes start with a 0. So I can output the C and continue with the next. Whenever whenever I read a 1 first, okay, I know this cannot be a C, so let's look at the next character and determine whether it's a 0 or a 1, and then continue this way. Okay, so if none of the codes is a prefix or is the beginning of another code, I can just read through sequentially. I don't have random access though, but I can read through it sequentially, and I can again decode the data. Relatively simple, right? All I have to do is to look up the bit sequence in a table. What I have to do is I have to transmit the table. So this codebook cannot be recovered during transmission. So I have to actually transmit this up front. So a Huffman encoded stream of data contains two pieces of information. One is the codebook itself, and then the encoded data. Now, for instance, the codebook is 8 bits, right? I have 8-bit characters, and encoded data is gigabytes of data. The transmission of the codebook is really negligible. So it's no big deal, but nonetheless, it needs to be transmitted along. Okay. So the question is, how do we generate that? I mean, well, I just said, okay, well, make this thing 0, make this 0, 1, and 1, 0. So I kind of made this up, right? But how do we generate that from the input distribution? And here's kind of Huffman in a nutshell. And the idea is relatively simple. So of course, we start with characters and their frequencies, and we throw those into a priority queue. So priority queue is a data structure that simply collects data, and when I say give me something back, it gives me the smallest or biggest element back, whatever I choose. Okay, so I upfront choose smallest or biggest. So here I choose the smallest. So I want the one with the smallest frequency, the rarest symbol, so to say. Okay, now what I do is, until I only have one symbol left in the priority queue, I do the following. I grab the first two, apparently there are two because I've got more than one left. I grab the first two and combine those. How do I combine them? I sum their frequencies up. So one shows up 10 times, the other one 20 times. I say, okay, well, the combined thing now shows up 30 times. And I create a tree out of those two where I say, okay, well, one is 1 and the other one is has 2, okay, or gets 2 as code. And then I add this thing back. I add this small tree with like this 1 and 2 branch. I add this back to my original priority queue. And I repeat this process until only 1 is remaining. Obviously, every time I grab true and enter 1, this queue shrinks by 1. So this whole thing will converge. In the end, I only have one entry. What do I have? I only have one tree that has branches to the left or the right with 0s and 1s to them. And those paths to the leaves, and in the leaves I finally have my characters, those are the Huffman codes. This whole thing actually sounds more complicated than it is. We actually implemented this yesterday in late night coding. And here's just the core code. So that's what I copied from yesterday's code. So this is just the Huffman coding part in regular C++. So there's a bunch of code around that. But the actual Huffman coding is really this simple. Okay, so here's the part that first takes all of those characters and adds them to the priority queue. So I just get pairs. First is the character, second is the frequency. So I just get as input pairs of characters and their frequency. And then in second step, until there's only one element left, I grab 2. So I grab 2 elements from the priority queue and I create one new with those 2 elements and push that back onto the priority queue. And well, I return the root element once everything has, once I only have one left. Okay, so that's pretty much it. It's actually super simple to encode. Again, there's obviously some code around that. If you're interested in the details, you can check out our GitHub repository for late night coding, or we'll continue with that on Thursday night, we'll continue the coding here. If you're interested in the actual C++ implementation, notice though that that's going to be in German, not the code, but the explanation is going to be in German. Okay. So nonetheless, let's just look at such a tree, what the tree will look like. So here we go. Let's say A is the most frequent character, and then B, C, D, and E are about the same, right? So A shows up 15 times, B, C, and D are roughly similar in frequency or in occurrences. Then this is the tree that I want to create, right? I want to create a tree where A that shows up twice as often is relatively short, and the rest, well, it gets about same length in bit sequences. Okay, the output code is shown here, and here you see the tree, right? So in that particular tree, well, here I am. We would call going left is 0. I mean, it doesn't matter. You can call this any way, but we'd say left is a 0, right is a 1. So if we start from the top, we go once to the left and end up at our A. So A will get the code 0. Now to get to B, we have to go left, right, right, I think. So which means 1, 0, 0, right? It's left, right. So apparently that is the left entry. So I have to go right, left, left, which is 1, 0, 0. And to C, I have to go right, left, right. So I get 0, 0, 1, and so on and so forth. So that's how you generate from this tree. That's how you generate the code. So you basically, to every leaf, you check where do I have to walk, and you turn that into a sequence of zeros and ones. Now, what you can also see is, first of all, that's a prefix-free code, because whenever I go one direction, that will never be part of another character's beginning, because, well, I took a detour, right? If I go left once, I'll never kind of go back. So, right, so I will have a 1 on the other side here. And also, it shows you that those sequences must be unique, because going left, right, left, right, left, right will create no ambiguity. So every path is unique. And that's it. This code here then has the properties that it's optimal, in a sense that you can generate no other code with integer bits, meaning 2 bits or 3 bits or 4 bits. You can generate no other code that would create an overall shorter sequence. You could technically create one with, I don't know, 1.5 bits. Okay, notice here that the B shows up more often than the E. So technically, we would spend a few less bits on B. I would like to do that and spend a few more on E. But since we can only use 2 or 3 or 1, we have to give them the same amount. So in integer systems, that is the best possible thing you can do. That's not saying that this is unique, okay? So for ones, I could just swap 0 and 1, right? I mean, I could just decide, okay, well, anything that's 0 here should be 1. And I would get the exact same length code and would still work. Or I could swap B and C here and D and E here. So it's not that this is unique, but out of the ones that give me the shortest length, it's one of those. Okay? That, by the way, is not to say that it's perfect. Okay, so you need to be very careful with the word optimal, because optimal usually has some sort of definition, right? Optimal here means that for integer codes, it's one of the shortest possible ones. However, it is possible to generate non-integer bits, right? 3.5 bits to dedicate that to a piece of data, and that's what's called arithmetic coding. So if you're interested in more detail on that one, you can just read arithmetic coding. It's a way more complicated technique, much more computationally evolved, but that actually allows you to spend, whatever, half a bit or so on data, and that's going to be better. So again, optimality is one of those things where you have to be a little bit careful. Yeah, it's a binary tree. Yeah, it's a path in a binary. Every sequence of bits is a path in a binary tree to a leaf node. Yeah, and the inner nodes don't contain any data. Okay. So what are issues with that one? Well, first of all, it's optimal. That's not an issue. That's good. If we stick with this optimality thing. There's one issue though that requires the knowledge of frequencies. Okay. As for this to work, we have to know, okay, how often does an A show up, or a B or a C? Now you could say, well, I mean, what's the point? I mean, just scan through the data, do a count. And that's pretty much what you would do most of the time. You would scan through the data and literally count how many A's, B's, C's we have. Now, it doesn't really work so well when we're talking about a data stream, right? If data is streamed to you, right, from a piece of hardware or from wherever, and you want to compress it on the fly, you don't know what's going to come. So You have to guess the frequencies then. So yeah, that's another thing you can do. Sounds like a pretty silly idea, and guess how often something will show up, but it turns out to be not such a silly idea in the long run. For various interesting reasons. So one thing is that if we've guessed the frequencies or we fixed them once and for all, we don't have to transmit them with the data. I said we need to transmit the codebook. However, if the sender and the receiver have, from the startup, agreed on a codebook, right? This is how often an A appears. This is how often a B appears. You don't have to send it because it never changes, right? It's part of the compression scheme. So that might make your data somewhat smaller. Now you might say, okay, but how could we come up with that? Well, here's the thing. So for instance, if we're talking about text, like literal writings, right, books, it's very well known for every language what the frequencies of characters is. For instance, I mean, spaces will appear terribly often, right? E's will appear, generally vowels will appear pretty often. So these characters actually can be determined in a pretty smart way. And for instance, that's exactly what JPEG does. JPEG has a codebook that is pre-agreed on. So it sounds like a pretty dumb idea, but actually the one image format that most of you use pretty much all the time, that's actually used during this very transmission here as part of the keyframes, is using exactly that. It uses a pre-agreed codebook, okay? So you can do a couple of other smart things like adaptively adjust the tree. So there's a ton of additions that you can do, but the basic idea is that simple and it works pretty well. Okay. And here's the thing, you can combine it with LD77. Remember LD77? That was the thing that generated these tuples, right? These 3 tuples. Now, if we first generated these 3 tuples, and that already crunches the data together quite substantially, but it might create these occasional 0 somethings. Now, what this means is you'll end up with a ton of zeros in your data. If you run this through Huffman coding, your zeros will become super small in terms of bits, and then they pretty much vanish. And this combination, so far, is one of the best known lossless compression approaches, right? Doing LD77 and Huffman pre-processed that. So that is what Zip uses. Technically, the zip format supports a bunch of other compression techniques, but it's pretty standard to use just deflate, and deflate is exactly LD77. Well, technically it's a variation of that one, but the basic idea is LD77 plus Huffman coding, okay? Plus a bunch of additional clever tricks, and even Zip supports this idea of pre-agreed codebooks. So Zip has a bunch of codebooks pre-implemented, 2 if I recall correctly, and it has the property say, well, we'll compute the codebook. And again, practice had shown that today pretty much any zip file that you will see has a codebook that's actually computed. It has a codebook that's actually computed by running through the data. But nonetheless, also Zip supports this. So if you want to write a full decoder, you have to implement those old codebooks that no one ever uses. Okay, back to images. PNG also uses the same idea, LD77, actually more literally LD77 without fewer variations, and followed by deflate, but prefixed by another idea called precoder. More on that in, well, I guess on Thursday. I'm not sure if we'll get there today. That brings me back to images. So again, where are all those things used? BMP, Windows, bitmaps, also OS2 bitmaps, but I don't think anyone uses OS2 anymore, which is a different format, just has the same name. Windows bitmaps in particular, they use either uncompressed data or they store in run length encoded, at least the first 2 versions. Later versions also support smarter encoding, but they're pretty unusual because you would then rather use JPEG right away. TGA, another popular format, again uses run length encoding. So that actually gets used, okay? GIF, as I mentioned, LDW, but with a bunch of quirks, so only 256 colors, can only do 8-bit. But since GIF 89A, it has 1 bit of transparency, yeah, so whether transparent or not. And it supports animation. And in particular has one thing that makes this very special. It has a bit that says, please repeat the animation indefinitely. Okay, and that's pretty much what made this format super popular. Was not just a stack of images, TGA also supports that, a stack of images, but GIF has this 1 bit in this animation byte. So that animation byte specifies how the animation is supposed to be carried out. how fast. And there's one bit dedicated to repeat indefinitely, which was just more or less of a joke as far as I read this. So it was more like, okay, sure, we have this one bit left over, whatever. Let's just infinitely loop these things. And that made these GIFs so incredibly popular. Also notice the 89 is again the year. So this is pretty ancient technology, right? I mean, what else do you use that is from the late 80s? But yeah, animated GIFs still are from the late 80s. So that's it. Next session, which is going to be Thursday morning, we'll look at PNG. We'll look at exactly how that works. In particular, we'll look at how this pre-filter thing works, or pre-filter. So that's something that is executed on top of LD77, on top of the Huffman compression. So there's yet another idea. And while this here is pretty general, again, Zip uses something similar, this pre-filter is very image specific. And that makes it such a great compression scheme for images. It's still lossless though. So if you compress something with PNG, you get the original image out with no loss at all. Compare that to JPEG, where your loss can be substantial, potentially unnoticeable or very hard to notice, but substantial. PNG is lossless. Okay. So that's pretty much it for today. Again, a reminder to those who actually listen to this stream and are my students at the University of Duisburg-Essen, please fill out the evaluation form. You can find this in the Moodle, on the Moodle page. It's underneath the YouTube playlist. We have so far, again, we have very few, we got very few forms returned. It's anonymous. Of course, it's voluntary. You don't have to, but I appreciate if you give us some feedback, positive feedback, or things that you would like to see changed in the future. This way you can influence how we do these things. Okay, so that's it for today. Again, we'll continue on Thursday, unless there are any immediate questions. And Q, remind me to make you moderator, so in the future I don't have to go and delete garbage from the stream. Since you happen to be here anyways, pretty much all the streams, remind me to just give you moderator rights if I haven't done so yet. Okay, so yeah, then that's it for today. Yeah, see you on Thursday. If you can and you haven't done so, get your vaccination. Keeps you healthy. Until then, bye-bye.